All right, we'll go ahead and get started. I'm holding the microphone, but it's not for your benefit. It's actually for the web audience. So, plus I just like to hold the mic. So I'm Dean Bickerton, the president of the ISA New Orleans section, and welcome to our second meeting of the year. We're going to have a few announcements here, and then we'll go in and kick off our technical topic for the day. So just announcements. We do have we still are in the middle of our sponsorship drive, asking for sponsors for our section. It's $150 to be a sponsor. We put your logo on the website, and we give you the opportunity to present technical topics at the meetings, or if you get first dibs at it, we'll put it that way. So we have new sponsors: Arthur Zadaran, ArtZad Consulting, Dennison Consulting Group, Process Solutions Automation and Control, and our speaker today, United Electric Controls, are all new sponsors for the section. And then we have some returning sponsors: CPU, Petrotech, Rockwell Automation, and the Reynolds Company. If you're interested in being a sponsor, when we're done with the presentation, we put the presentations and the recording of the session up on our website, so you can pull down the session and all these hyperlinks will be live. So you can go there, hit the hyperlink, or just go to our website and hit our sponsor page. And there's information on how to sign up, and you can do all your transaction and everything right there from the page. Upcoming events: there is an event that's going on tomorrow that we helped promote. It's Manufacturing Day, so technically this Friday is Manufacturing Day. It's a daily event that's held annually, sponsored by the NAM, which is the National Association of Manufacturers. So all across the country this week there will be various tours going on of manufacturing facilities for students. So the whole purpose of Manufacturing Day is to get students involved in manufacturing and get them aware that manufacturing is a good career. It's not dark, dirty, and dangerous. It's a good career. So so you'll see a lot of on the NAM website. You'll see students touring various manufacturing facilities across the U.S. So what we're doing here is Dennison Consulting Group, which is one of our sponsors, got together with some local manufacturing and put together a day at Tulane. And so we have, I got another slide on this. We'll go into a little more detail, but that's tomorrow. If you want to drop by, feel free. And then our next section meeting will be Tuesday, November 7th, and the topic for that one will be improved protection with wireless heart gas detection. And actually, our sponsor for today will come back and have one of his cohorts present that topic next week. So it'll be United Electric Controls. We'll be doing that topic as well. All right, so the Manufacturing Day tomorrow is at Tulane University from 8:30 to 3:30. It's at Kendall Cram Lecture Hall, which is room 213. Again, sponsored by Dennison Consulting Group and the NAM. And there'll be presentations throughout the day, kind of on the hour, and some panel discussions over lunch by Dennison, NAM, the ISA. We'll have a couple people there. Wayne and Bill and myself will be there representing ISA. Our company, the Reynolds Company, Georgia Pacific will be there, NASA, Boeing, Lockheed, and Graphics Packaging. We had the STEM Fest. We've been Core Element, which is a local group, sponsored an activity called STEM Fest. It was the first inaugural event this year. It was held at the St. Pelicans training facility over there on Airline. And for an inaugural event, it was very well attended. My daughter goes to Dominican, and she's on the robotics team. So I went there to pick her up, and I went a little early just to kind of check it out and see how things went. And they had about 2,000 students come through, looking at interest in science, technology, engineering, and math. So you had people like Oshner, Lockheed, Boeing, various high schools, some of the colleges, local colleges, all had exhibits set up and activities for the kids. So it's a real good way to get them excited. Microsoft was there, brought a few Xboxes so the kids could play Xboxes, and I need to get one of those little cases. That's pretty cool. And there was a special appearance by Pythagoras himself. He attended. So, that's Martin Patterson with W.S. Nelson. So W.S. Nelson was out there. They had a booth set up on indirect measurements. So Mr. Pythagoras was there. All right. Other announcements, we have the Fall Leaders Meeting is coming up end of this month in Tampa. There is a Process Control and Safety Symposium and Exhibition going on in Houston next month, November 6th through 9th. That actually coincides with our member meeting on the 7th, but that's going on next week. And then the International Instrumentation Symposium is co-locating with the Safety Symposium, and there's a special deal there. If you register for the Safety Symposium, you can attend the Instrumentation Symposium for an extra $100 if you like. All right, and with that, I will turn it over to Mr. Channing Reese, who will talk to us about hybrid safety logic solver solutions.
Thank you, Dean. Could I have that clicker?
Oh, you can have the clicker, yes.
Thank you. Well, I'm reminded that in the old days we used to take a lot of money out of our advertising and promotion budget. Great, and that money used to go to the National ISA for events like the ISA shows, the large ones that they used to host in Houston and alternative years. I'm trying to remember now where the northern venue was. Yeah, New Orleans and sometimes up in New York, I think. But that's changed, of course, like a lot of things in this world. So this opportunity to speak in front of an ISA section is really a great privilege, and it's a great way to really get closer to end users, I think, apart from the large shows that we used to participate in. Anyway, to our topic today, this subject of safety transmitter logic solver hybrids. The notion that you could take a device and sort of make both a sensor and a logic solver out of it is something that we've been noodling around for a long time. And back about 4 years ago, we started, actually long before that. The earliest iterations go back almost 20 years, but the SIL certified versions are more recent, and we're going to talk about that today. So we might begin this discussion by giving some examples of the traditional sensor portfolio. It might be a process transmitter. It might be something like a process switch. It might be a trip alarm or a trip module. So you can see in just these three products alone, the building blocks of a critical loop, right? And we won't go into the final elements because this is where our focus is on the sensor part. And today's topic specifically is about this safety transmitter switch, or this hybrid. What you call it has been something of a little bit of a head scratcher too, because customers are usually thinking either of process transmitters or switches and not the combination of one in the same kind of footprint. And that's what I think several years ago one of our competitors came out with a product like this and called it a hybrid, and it seemed to be a good way of representing it. So if we look at just the process transmitters, they're obviously widely accepted in basic process control and in this area called SCI, safety controls, alarms, and interlocks. They supply a 4 to 20 milliamp output as the input to the critical loop. They come with or without indication, and the interface or the integration is dependent on that logic solver, that central logic solver. And the attention to setting it up, commissioning it, making sure that the configuration changes are intended and not unintended, and the issue of proof testing is something you have to take care of. They're still capable, so if you look on the safety automation equipment list, for example, that Exida hosts, you'll see a lot of process transmitters up there. They've been around long enough so they meet this criteria that the functional safety standards have defined called prior use, but there are certified versions as well. And the newer versions of these process transmitters have dealt with that issue of frozen impulse lines, because that used to be a concern, right? In fact, it's still a concern because there's a huge installed base of transmitters that still can't detect frozen impulse. You get a frozen 4 to 20 milliamp signal, and it can be very dangerous, right? All right, so now we go to the switch. Again, widely used in safety control, alarm, and interlock, not as much in basic process control. In this case, a Form C output, single pole, double throw, using traditionally a micro switch. No indication. The interface, the integration is discrete, right, to the logic solver or to some final element directly, because it has the capacity to handle the final element kind of switching. Same issue with setup and configuration. It takes attention to detail. In this case, a few more wrenches do, and probably an equal amount of time, if not more. These devices are still capable now. Like many devices, electromechanical and solid state, they have met the requirements of the functional safety standards, which combine not only the manufacturing process and the development process, but also the implementation of the design and the development. So you'll see SIL certified electromechanical switches now on that automation equipment list. As far as this trip alarm, trip module, same thing, SCI implementation using sometimes analog inputs and digital outputs with or without indication. Those things, those safety trip alarms require more environmental protection generally. So, it's got a different environmental profile than does a process transmitter or those switches. And they are still capable. With a footnote, you've got to monitor that process output with a diagnostic output. And it's not automatic. It's something that has to be implemented. Okay, so now we move to the topic today, which is this hybrid idea that you could squeeze some of this together in one footprint. This is, as best I can describe, an emerging niche, right? Not all customers will implement a device like this in a full-blown safety automated safety instrumented system. So this word niche has come up a lot, and I've heard big operators use it to describe ways in which they think this can be used very effectively to protect certain loops. It combines the functions of a transmitter and a trip alarm. It does so with indication. It can be coupled to the logic solver, or it can be powered externally. So it's got that flexibility that a process transmitter doesn't. It is still capable. So the one you're looking at right there is certified to SIL 2 with SIL 3 capability. And we've gained this prior use acceptability with this particular design as well. So that root, what they call root 2H. And it has automatic self-diagnostics. So the manufacturers of hybrids are paying attention to this imperative for diagnostic coverage. So if you were to create the value proposition for this hybrid, I guess you'd say it's cost effective. It's got the advantage of this 3-in-1 footprint. I guess 4-in-1 if you included the gauge. It has a lower price point. If you compare just the unit costs of certified devices, SIL 2, this is about a half the unit cost of a typical SIL 2 certified process transmitter. It can be simply integrated because it's not dependent on that logic solver for its powering or its functionality. So there's a lot of options, a lot of flexibility for integrating it, in a local fashion, and it's still capable. Okay, so that would be the argument for considering a device like this. The certification is not a small one. This is very important, of course, because as new technology advances, and it's advancing rapidly, sometimes the path for manufacturers that want to get this out is to go to the certified route. And same thing with the users, right? They want some objective way of implementing stuff, sometimes quickly, sometimes without the type of prior use validation that is demanded. And so being able to lean back on a device that's been certified to the functional safety standard is an important path. Okay, so let's just talk about that for a minute, the functional safety standards against which these devices are measured. So it's both a qualitative and a quantitative assessment, really. So IEC 61508, which is what they call the mother standard to which a lot of these devices are measured against, has spun off these derivative standards, right? And this one over here, IEC 61511, is for the process sector, so that's most of where we play. This machinery standard, too, is very closely, it's very closely aligned, too, in the sense that you find a lot of machinery in plants, right? And how do you protect machinery, and how do you protect workers? How do you protect the environment when machinery is deployed, right? And they focus on that using something that's equivalent to a safety instrumented system called a safety-related electronic control system, usually, this SRES, which so a lot of manufacturer refiners, for example, or compressors, or other rotating equipment might look there. I've seen less sort of examples of that in the safety machinery area, but I think it's probably coming. All right, ISA also has standards. In fact, when IEC was developing 61508 many years ago, ISA was too, with this companion standard called ISA 84, right? And it, I don't know, IEC got to the finish line first, I guess, in terms of publishing it, but the ISA folks, of course, the committee that developed the 84 standard had put a lot of work into it as well, and saw the wisdom of harmonizing these standards. And so this got published as ISA 84 back in 2004 in its first edition. And it's the same as the IEC 61508 standard, with the exception of a grandfather clause. And this is being updated as we speak. So the ISA 84 committee meets next week in Houston, and they've got several working groups that are looking at different elements of functional safety, fire and gas systems, and this notion of SCI, safety controls, alarms, and interlocks, and the standard that applies to that, and others. So that's ISA's contribution, which is significant and continuing. If we kind of summarize this idea of a process sector standard, this one that governs electronic and programmable electronic devices, functional safety is a concept applicable across all industry sectors. It is fundamental to the enabling of complex technology used for safety-related systems. And it provides the assurance that these systems will offer the necessary risk reduction required to achieve safety for the equipment. That's the committee's words. And they deal with active systems, not passive systems, right? So the detection of smoke by sensors would be an example. The activation of a level switch would be another example. Active system. So these are the standards against which these devices are measured. Now, this is an interesting one, right? Because you probably have heard less of this standard here, called ANSI ISA 8491. It was a 16-page standard that came out in 2012. It was really Angela Summers that called people's attentions to the importance of mechanical integrity of safety controls, alarms, and interlocks. So she's been the champion of this and has a lot of support, both among users and among manufacturers such as UE. The standard establishes a procedure to identify the process safety functions that utilize instrumentation to maintain safe operation. And they call this SCI, Safety Controls, Alarms, and Interlocks. So this is a discussion separate and apart from safety instrumented systems. This is everything else in that instrumented world that's easy, I suppose, to overlook, right, in a plant. And the concern about mechanical integrity and maintenance of those systems, those instrumented safeguards. And in that standard, well, I'll go over the basic concepts and then I'll show you a little diagram. So just in summary, to identify process safety functions that utilize instrumentation to maintain safe operation. It's called SCI, Safety Controls, Alarms, and Interlocks, including SIS and emergency shutdown. And that'll become clear in just a minute. And focused on the mechanical integrity and maintenance as the gateway to improved managing process risk, improvement. Again, this is only a 16-page standard, but it sort of calls attention to these process safeguards apart and separate from the functional safety standards, S84. So this whole laundry list on the right, safety alarm, permissive, safety critical control, safety interlock, safety instrumented systems, aha. So this is merely a subset among this whole group, emergency shutdown, detection and suppression. Now this is good news for manufacturers of switches because, you know, apart from safety instrumented systems, this is where a lot of work is done, you know, and through all manufacturers of these building blocks of a loop, right? And Angela has written about this as a good white paper that she's published called Safety Controls and Alarms and Interlocks as IPL. So she wants to integrate this discussion of SCI with the notion of independent protection layers, which is what they are, really, if they're implemented properly. So I would recommend looking at that because it's a really interesting white paper where she explains or reviews, you know, the ways in which basic process control are implemented. So here's a typical loop, right? Sensor, control, logic, solver, final element on the left, and on the right, this trip amp that we spoke of, right? Sensor, trip amplifier, final element. That's in the BPCS world. Same thing is true in safety instrumented systems. Sensor, logic solver, final element. Same thing over here. And we have a lot of chemical and petrochemical plants that are coming to us talking about this implementation, which is sort of the poor man's way of implementing SIS, because it involves, it's more distributed, it's less expensive, it's more local, right? But it's still considerable. It's a considerable effort because you're not free from the obligation in a safety instrumented system of implementing everything, you know, that a full-blown safety system would involve. So that's recommended reading. And just to summarize what Angela says, when considering the use of basic process control systems for SCI, for those process safeguards outside, but to include the safety instrument system, the first thing to remember is that risk reduction ain't free, and that getting an order of magnitude risk reduction is hard. The independence and reliability requirements impose rigorous design and management practices focusing on eliminating single points of failure and human error. So it's looking at the systematic errors, it's looking at the design considerations. And when claiming more than one order of magnitude from a single controller in a scenario, the controller must be designed and maintained in compliance with the process safety standard, the functional safety standard. So I think if you were advising new people on this topic, right, and you threw the 3 parts of the functional safety standard at them, and that would take them several months to get through and to understand. This standard on SCI, 16 pages, but it sort of deepens and broadens one's view of this whole topic, you know, because there's an awful lot of landscape out there that doesn't include a dedicated safety instrumented system that has to be taken care of, has to be maintained, because it can put a demand on the safety system, and that's the concern, right? When it doesn't work upstream of the safety system, that's a problem, right? Because it places demands, right, on the safety system. Okay. All right, so we're now going to take a look at just a typical, maybe traditional recipe distributed SIS involving some of these sensor components that we talked about. So a process transmitter, trip amplifier, safety relay, commanding a final element, right? This was given to us by an EPC in California that had looked at hybrids and said, well, that's kind of interesting because I know what the traditional architecture looks like, and I know what it costs both to implement and to maintain. And the idea is that you can get rid of the process transmitter, he was saying. You could get rid of the trip amp, you could get rid of the safety relay, you could get rid of the wiring, some of the programming, by implementing this hybrid, which can not only supply a 4 to 20 milliamp output, but it can command the final element using its digital output, which in this case is a relay that's high capacity. It could be either, you know, a AC relay or a DC relay, all in this little package, which is about the size of a typical process transmitter. It can even supply, you know, for those that are using turbine controllers with that black start standard 125 VDC, it can even supply a switched output, right, to at this electrical standard. So it's pretty flexible. Now these in the case of this hybrid, these are 3 different model numbers, right? But everything else is the same. It's programmable logic, combining the notion of a switch, a logic solver, and a transmitter. In a functional safety context, okay, we look at target SIL, we look at PFD average, we look at risk reduction factor, and now let's take a look in this context and in the context of hybrids and other devices of, let's look at a theoretical SIF. This really came out of an earlier SIL verification summary that I was familiar with, that was, you know, this modeling of devices in a high pressure protection SIF, and that's the description of the SIF, measuring steam pressure in the boiler output header and opening a vent valve. And if we look at the sensors, okay, these are the assumptions, right? The sensors were either, in this modeling, were either certified process transmitters or this hybrid of a switch and a transmitter and a switch, excuse me, a hybrid of a transmitter and a switch. In clean service, the mean time to restoration was given as 24 hours, proof test interval of 12 months, proof test coverage is assumed to be 100%, unrealistic, but this is a theoretical modeling, and the process outputs are assumed to fail to safe states. Okay, the sensor, sorry, the logic solver. It was a generic SIL2 or SIL3 logic solver, mean time to restoration 24 hours, proof test interval 60 months, extended out as you can see, and proof test coverage again assumed to be 100%. The final element in this modeling, a generic three-way solenoid valve, a pneumatic spring return actuator, a easy valve, a mean time to restoration of 24 hours, back to the 12-month proof test interval, and proof test coverage that was assumed to be 85%, and no beta factor. So the beta factor is that common cause burdening that is applied where devices of similar manufacture, right, similar design are used. So this was what Exida had set up as a theoretical SIF, and the simplified equation is the probability of failure on demand average is equal to the sensor subsystem PFD average plus the logic solver PFD average plus the final element PFD average. Now let's bring this back to the actual devices, some of which we have looked at. So this comes off the safety automation equipment list. So if you go and look at that Exida list of certified instrumentation, there will be a description of the device. There will be a statement of the safety variable output. the architectural constraints. So these all come off the certificates, right? And then in the case of these process transmitters, the 4 to 20 milliamp output has this PFD average. And if you look down here where this hybrid is, this likewise would have a PFD average for the 4 to 20 milliamp output. But we're not interested in that comparison as much as we are with what the relay does. Okay, so it's interesting that when you sum up the PFD averages of the analog outputs, right, and you jump here to the PFD average for the safety relay, right, as we described in that hybrid architecture, right, the risk reduction jumps here by twice. And actually gets to SIL 2, right? So the question is, why does that happen? Is it simply a relay is a better component? Is it better PFD average? Well, no, actually, it's the same order of magnitude, but you can see here it's not quite as good as that, although those numbers are very close, right? So does anyone have an answer to what the reason is that that risk reduction factor would jump by twice, more than twice? Well, these are 1 out of 1 systems, right? This modeling is 1 out of 1. So there is no redundancy shown. Yes, well, right, but there's something else.
How do you determine an output without utilizing a logic solver? The risk reduction, you zero out risk, that means you remove the logic solver from the equation.
Right. You've removed it from the equation, that's true, but you haven't removed it from the architecture because it's still being employed, right, to power the unit. Yeah, it's still being used to power the unit. It's still being used to monitor the process variable.
Then you should be able to remove the logic solver from anything above it based on effective.
Exactly. And you see this number is 0.
But anything above that should also be 0 because the 4 to 20 milliamp current also resumes the same function. Every device above that has a 4 to 20 milliamp function.
That's right. And so the logic solver, sorry?
See how you break out the logic solver from the 4 to 20 milliamp current above, but then suddenly assume no logic solving for the 4 to 20 milliamp current on that device.
Well, not for the 4 to 20 milliamp, but the power here, right, used is exciting that relay output. Okay, and the fact is that only one safety variable output is contemplated to control the final element. So it's not where we average these, right? Although some safety designers might argue that, right? If you're depending on the power, right, here to do this, right, you've got to model this as you do these, the power supply, right? So that's where the risk is in terms of the power requirement for this architecture. But in terms of the calculation of the PFD total, right, you're only counting one safety variable output, right? This relay is what's commanding the final element, right? It's interfaced directly with a solenoid valve or a motor control starter. And if you look through the FMEDAs for these products, you'll see stated in there.
Okay, so logic solver is independent of the device. You're taking that and replacing the safety relay and logic solving within the device as a single item.
Right.
Sometimes
Yes, exactly. The logic solver really lives over here,
Okay.
right? And well, it lives in all these red numbers, right? It's as if you took these numbers and this and added it together, and
It's one
yeah,
order of magnitude
better.
better than the logic solver.
Yeah, it's showing up here, right, as 4.85 times e to the minus 3, and it's, which is what's allowing it to get to SIL2 as a standalone device, because this risk reduction factor, the inverse of this gets to SIL2. It's a head scratcher, I realize, and that's you know, we've had some difficulty explaining this, you know, because it's not traditional, you know. So this number goes away, and now this gets added up. So I can think of one large operator, for example, that's using this in upstream applications where they want to replace, they want better control over the flow line. They want better control over killing the flow of this upstream well. And they want risk reduction. They want to achieve a certain level of risk reduction. And the idea is that they could use that relay coupled directly to a 12-watt solenoid valve to close down and shut off this well and protect piping, you know. And they can get faster response time out of this relay, something in the order of 100 milliseconds better response time, which now this hybrid also, in addition to having an analog output, has two of these digital outputs, and this one is what they call a photo MOSFET, a metal oxide semiconductor field effect transistor. It's just an electronic switch that likewise is driven by the programmable logic in the device and mimics. So these settings mimic one another. This also gets to SIL2, just barely. But now this looks at just a SIL2 logic solver. The SIL3 logic solvers, right, this number here improves by 2 orders of magnitude. And when these numbers get rolled up using a SIL3 logic solver, these numbers become almost the same, right? You get improvement here in the risk reduction factor for the process transmitters. This stays the same, although there's some improvement here too, because there's improvement in the digital channel of the logic solver too. When we looked at this about 5 years ago, we found significant risk reduction using significantly different risk reduction using the digital I/O, which is the nature of logic solvers. The analog was burdened a little more. Here's an example of how, you know, the traditional approach might be with a SIL2 safety instrumented system and a positive displacement pump, right? Process transmitter to a safety PLC to the MCC, right? And what this doesn't show is this is in a stainless steel cabinet. You know, that's another $10,000 and a sub panel. And the challenge, even in this application, was process safety time. The designer, who was Mustang, was looking for process safety time of greater than a second. And the hybrid uses the relay in this same architecture directly to the motor control start-stop circuit, and then can get monitoring out of the device if that's desired. So that's one of these niche approaches where there's lower total cost, faster process safety time, less programming. Is a hypothetical example of a voting system, right, where you have 3 process transmitters commanding 2 valves through a single logic solver, and the safety designer was telling us that this wouldn't provide enough risk reduction in this scenario. They were looking for some very significant risk reduction north of 8,000, and the beta factor alone, right? The common cause beta factor would burden this. I'm a little out of order here. This is what I wanted to show you. So the idea is, if you were to put in the hybrid and use the safety relay output from the hybrid, that maybe you could justify this as an independent protection layer. That was the notion. And call the other loop another independent protection layer, IPL2. Now, back up for a minute because I wanted to show you this. So this was an ISA presented paper about 2 years ago at that same safety symposium that's taking place in November, the international one. And this was a fellow that, by the name of Henry Johnston from Genesis in Houston. And part of his argument in this paper was inspired by this hybrid notion, right? And it's illustrated in this simplified process diagram. So you have 15 wells here, I guess, coming into a common manifold and a flare system, and then a safety system downstream to protect the piping, involving a traditional voting architecture with 3 process transmitters. But this was going to be more daunting up here, how to validate the risk reduction here. They had it here where they wanted it with a low pressure piping, but upstream, this was going to be a real problem for the client, getting the kind of risk reduction that they wanted. And they made an argument in this paper of how you could do it. And it doesn't involve just our device, or our hybrid, shall I say, or a hybrid. It involves this notion of a separate independent layer of protection that would command this solenoid valve. And it's represented here as PS, pressure switch, and pressure transmitter. And the circles aren't joined, but he told me when he wrote the paper he was thinking of that hybrid device where you could you could get the risk reduction in combination with other things they were doing, including sizing the flare differently. So I would recommend that paper as well. And again, only parts of it really relate to this hybrid argument. And when he uses hybrid here, he's speaking of it in a larger context, not just our device or a device. That's a hybrid. Okay. I'll skip ahead. This is just a chart that's meant to do a rough comparison of attributes. So the hybrid we've been talking about has these kinds of specs: a very high safe failure fraction, 98.6, safety accuracy of plus or minus 3%, fault detection time, very rapid, 6 seconds. These safety variable outputs in this hybrid, every one of them is qualified by Exida as a safety variable output. That in itself is quite unique, and it invites some flexibility. This is a very, shall we say, high-end process transmitter. The safe failure fraction is 95, plus or minus 2%, 30-second fault detection time, one safety variable output, the analog 4 to 20, and a similar environmental profile. So these come off the FMEDA of these devices. The triple arm we spoke of, diagnostics not quite as robust, 2% safety accuracy, 15-minute fault detection time. This footnote that assumes that the fault relay is wired in series with process relays for fault monitoring, and a pretty optimistic mean time to restoration. Wrapping up here, the question is, can hybrids address common cause? And this was a good report that came out in May of 2015 by Syntef, whose clients mostly are, I think, North Sea clients. It was about the subject of common cause and beta factor. And if we jump to one of the summary pages, we see this list of equipment, these major equipment groups. This Syntef report was based on actual field failures that could be attributed to common cause. Again, common cause being that phenomenon of a device of common design, common manufacturer that would fail, in a similar mode. And these beta factors over here, right, that come out of the older handbook, right, and are informed oftentimes by manufacturers, give a beta factor of 6% for process transmitters. But the new beta factor they're recommending based on these failure reports is much harder. It's 15%. So they consider these figures over here to be very optimistic. And this is a factor that you would apply, right, to the PFD average on the question of cell achievement. To my audience, I apologize for walking in front of the screen. Okay, summarizing the benefits of hybrids: highly distributed SIS, right, where full-blown safety systems are cost prohibitive, where ESD and continuous monitoring are needed in combination, where process safety time thresholds cannot be met, right? The relay and the programmable logic on the hybrid is going to be faster than that processing that goes on through a loop, again, depending on the loop, and where diversity can reduce common cause. Finally, cost is a big consideration for a lot of users, and the argument here is that lower unit price points for the certified devices are desirable, and total cost solutions are imperative, and that's driving a lot of interest. And I thank you for your attention. Any questions I can answer? I'm happy to.
Approximately price difference between a regular transmitter and one that's a hybrid.
Well,
times the cost.
Well, the hybrid that I'm speaking of is about $1,000 list price, and I think most of the certified SIL2 process transmitters would be $2,500 or higher. We have a sample of it back there, so you can get an idea of what it looks like, and literature. Any other questions? Yes, Arthur.
On the programming part of it, how actually do you physically program it?
It's done through a keypad, so it's a class 1 div 1 enclosure, but you remove that cover, all right, and the programming is done on a keypad. The setting of the set point, the setting of the deadband where it resets, the setting of other parameters like you can put in a digital, you can filter a spike, so it has a digital kind of filter. You can latch those relay outputs. So if a manual reset is called for, you can latch them. You can reset the minimums and the maximums. So the device, stamps the minimums and the maximums that are occurring, so that an operator can come by and look. And you would reset those minimums and maximums using those keypads. It has no bidirectional communication, so we were convinced in the design of our hybrid that that issue of unintended configuration changes was a large enough systematic concern that where safety instrumented systems or other safeguards are involved, not to allow any kind of handheld communication with the device or remote configuration. So the setup is all done on the keypad.
Is there a way to document the setup for record-keeping purposes?
Yes, well, because it's a certified device, we have a safety manual. Do you mean on the software?
Yeah, you've configured it. Is there a way to record the configuration for posterity?
No, not on the device itself.
Or you can verify that that's what's in there.
Yes, when.
Later,
Yes, I see what you're. Yes, if you go by the device again, your system would have to be in bypass, right, to be compliant. But if you remove the cover, you can push one of those keypads and see what the setup is. You can see what the set point is, the deadband, the switch mode. It always de-energizes to trip, but the mode can be either on rising pressure or falling pressure.
You can't suck that out electronically.
No.
Yeah, hard. You can't enable that hard.
Well, it's not hard enabled. Yeah, so it's for the reasons I just explained, that people were concerned enough, the designers we talked to, about unintended configuration changes.
So how do you access the diagnosis?
Well, the outputs fail to a safe state, so the analog output would fail to that NMOR standard, 3.6 milliamps, right? The display on the device will display any faults should it fault.
That's like
After something
it's not
faults.
predicting, it's not proactive.
There's no predictive diagnostics on it.
So every system has to be tested on some interval.
Right.
So nothing short of a full-blown test is possible. That's what it sounds like.
To cover that part of the safe failure fraction, okay, that figure I showed you, 98.6, is Exodus confidence about how much coverage the device will provide in an automatic way, 98.6. The residual faults, right, that small percentage other than that, right, have to be, like any device, have to be rooted out by proof testing the device at some regular interval.
Require a full-blown proof test.
Yes, and that's true of all sensors out there.
You can't extend that interval by doing, like you can today. You have devices that have onboard diagnostics and safety elements that have some capability for diagnostic coverage by doing partial stroke. You can extend your test intervals
Right.
without having to do a full-blown test of the entire safety system.
Yeah.
With no access to the online diagnostics, there's no way to do in situ type testing on this device.
Oh, yes, there is. You can walk by it, right?
Mm-hmm.
And as I said, if there are faults, right, they're going to be displayed on that front.
Well, if there's a fault, then already you have a contingency plan that has to be implemented, because now you have a part of your safety system that's in fault.
Right, exactly. So what you're referring to is the proof testing that has to be done, right?
To extend the interval, I'm trying to run my plant for 12 years.
Yes, right. And so you'd want to pay attention to that safe failure fraction, right? Remember those figures over here that represented the percentage they call safe failure fraction.
Mm-hmm.
And that's the certifying agency's statement of how robust the diagnostics are. And so the hybrid had something in the order of 98.6%.
That doesn't get me to 12 years without a full proof test of that
No,
safety system.
no. And again, the proof test coverage is going to be, the proof test intervals are going to vary by plant and by what the process safety folks have determined is necessary. I think what you're saying is like a valve, right? You could go to this device or any device, right, and put it through tests, right? Put the system in bypass. You could alter, for example, the set point on the device to see what happens to the relay and how it causes the valve to open, right? You can put it through other checks in situ right there, but you can't do it remotely if that's what you're asking. Any other questions? Thank you very much.
Thanks, and we'll conclude this month's session. And thanks for everyone that attended via our web audience and our live audience. And we will see you November 7th for our next session. Thanks. And scene.